Hello and welcome again to my physics online video lecture supplement series. In today's video, I wanted to look at the beginnings of the 8th set of lectures for my introductory physics courses, which pertains to momentum. And specifically, I'm going to start actually by making reference to a demo which I have done before in class, and which I have on a different video that I've made. And in this video, we basically drop two balls so that one ball is positioned directly on top of the other ball. And the question is, how much higher does this little ball bounce, the one that's on top bounce, than it would have if we just dropped this ball, assuming that no energy is lost from the system, etc. So you can actually do the demo yourself at home if you have like a basketball and a racquetball or tennis ball. Or you can go watch one of my videos or look up any number of other videos online that show what happens. In any case, the answer is that the ball will bounce about 9 times higher than it would have had it just been dropped alone. And of course, the bigger ball actually bounces a lot less high than it would have otherwise. So that little question and that little demo is what we might use to jump into the topic of linear momentum and ultimately conservation of linear momentum, which are parts 1 and 2 of this set of lectures. So today I want to talk more about linear momentum than anything else. And linear momentum is generally a useful concept for describing objects which are in motion. And what it is it's basically a quantitative measure of the object motion. Recall, if you will, that when we were talking about in lecture set number, I believe it was lecture sets 5, the lecture sets on forces, that I introduced the Newton's first law and the formulation of it by Jean Buridan. And in that formulation, he discusses how all the stars and planets in his cosmology, particularly the planets that he was observing in our solar system, came into being with a particular quantity of motion which they retain on account of having the ability to move through space where there is no friction or other dissipative force. So this quantity of motion, one form of a quantity of motion would be momentum. Another form we'll find later is also called angular momentum. And this is basically a useful quantity. In particular, linear momentum is a useful quantity for analyzing collisions between two or more objects. And actually, that simple demo or thought experiment is basically a series of collisions between the big ball, the little ball, and the ground. We can also use this concept of linear momentum to discuss things like rocket propulsion, or if you were to fire a gun, for example, there's an expanding gas from the bullet that propels it forward. That can be analyzed in terms of work, but it can also be analyzed in terms of momentum. And then, last but not least, we can talk about changes in momentum. And so a change in momentum is sometimes called impulse. And as we'll see later on, Newton's second law can actually be formulated in terms of change in momentum per unit time. So let's get a nice definition for linear momentum before talking about all this other stuff. The linear momentum is the product of the mass, the speed, and the direction. In other words, it's it's the product of the mass times the velocity of an object. You could think of it as how much stuff is moving, how fast is it moving, in which direction is this moving. So this is the definition in equation form. Momentum, we use a lowercase p, and so p is defined as m times v, mass times velocity. So another thing that's worth noting here is that the larger the mass you have, the more momentum, and then the larger the speed you have, the more momentum. So these two objects actually have the same momentum, even though this one is much smaller because it's moving faster, or even though this one is slower because it is much bigger. The other thing to note here is that the larger momentum that an object has, the greater amount of force that is going to need to be applied to that object in order to stop it in a given time. And you can see that because in order to stop something in a given amount of time, you would have an acceleration here. The larger the momentum, the larger either the mass or the velocity. And if you have a larger velocity, then you're going to need a larger acceleration to stop in the same amount of time. If you have a larger mass, then you're going to need a larger force to get the same acceleration in the same amount of time. In any case, the SI unit for momentum is the kilogram meter per second, and it can also be reformulated in terms of other quantities like newtons, for example. So force is actually a change in momentum per unit time, so it would be a newton times a second. Also gets you momentum. So let's look at a few basic properties of momentum. It is a vector quantity. That means that although there's a magnitude, which is the product of the mass times the speed, there's also a direction, which actually is going to be the same direction as the velocity itself. If you have multiple objects moving, then the momentum of the system is basically the sum of the momentums of the individual objects, and is also equal to the center of mass momentum, if you will. Center of mass momentum basically could be thought of as the almost weighted average of the velocities, where you're weighting using mass. In any case, the center of mass velocity is going to give the same direction as the system momentum. And so because momentum is a vector, it can be broken into components like px, py, and if you're in 3D, you can also have a pz. And so here's a simple diagram showing the total momentum of some object with the x and y components of that object. It also, in scalar form, can be related to the object's kinetic energy. So the momentum squared divided by twice the mass is going to give the kinetic energy of the object. This is, of course, the magnitude of momentum squared. And that's true as long as we're dealing with objects in the classical physics regime. So macroscopic objects that are not traveling near the speed of light or in a very, very, very large gravity well. So let's look at a few examples to put all these equations to use. So suppose you have a 500 kilogram car which is moving with a speed of 15 meters per second, 30 degrees east of north. What is the car's linear momentum? All right. The momentum is going to be given by the mass times the velocity. So this is going to be mass is given as 500 kilograms, and the velocity is given as 15 meters per second in the 30 degrees east of north direction. So we would write that as maybe north 30 degrees east. And so the total momentum, 500 times 15, should give us 7,500 Newton seconds, comma, north 30 degrees east, where Newton seconds again is the same as kilogram meters per second. Our second example sort of builds off of the first one and asks, how can you convert the momentum that we found in the first part into Cartesian coordinates, with east being positive x and north being positive y? So this is the momentum that we found at the end of the last problem. Might be worth drawing for ourselves a little diagram of what this looks like. So here's our object. The momentum has a magnitude of 7,500 Newton seconds in this direction, and basically this direction is 30 degrees east of north, so this angle right here is 30 degrees. So if we wanted to split this into x and y, then we can either figure out what this other angle right here is, which would be 60 degrees because these two are 90, and then use our sine for y and cosine for x, or we can take this angle and use sine for x and cosine for y. Either way should get the same result. So in the x direction, we should have p times, let us say, the cosine of 60 degrees. So that is 7,500 Newton seconds times cosine of 60 degrees. This right here has a value of 1/2. So we're looking for a half of this 7,500 number. So px should be 3,750 Newton seconds. Similarly, for py, we would use p times the sine of theta, this guy being theta, this guy being basically phi. So that's 7,500 Newton seconds times the sine of 60 degrees. So sine of 60 degrees should be square root of 3/2. It's a little easier to just use the calculator at this point. So 7,500 times, we can take the sine of 60 and get 6,495 Newton seconds. So 6,495. So in Cartesian coordinates, therefore, the momentum might be expressed as 3,750 Newton seconds, comma, 6,500 Newton seconds, under the assumption that we have three significant figures. And in fact, since we have really two significant figures, this one right here probably should be written as 3,800. So that's what our momentum is going to be in Cartesian coordinates. Third example, and this is using the other set of equations, namely this one. Suppose you have a ball whose kinetic energy is 125 joules and a linear momentum of magnitude 11 kilogram meters per second, or in other words, 11 Newton seconds. What's the ball's mass and what is its speed? So let's see how we do that. All right, we have right now that EK is equal to P squared over 2M. So we're given right here the value of P. We're given right here the value of the kinetic energy. So we can rework this equation by solving for M. So multiply both sides by M, divide both sides by EK. what you end up with is that the mass is the magnitude of momentum squared times twice the kinetic energy. So that would be 11.0 kilogram meters per second quantity squared divided by 2 times 125 joules. And so the mass of this object should be given by, let's pull off the calculator for this. So we go 11 squared should be 121, divide that by 2, and then divide that by 125. And we get 0.484. And since everything is in kilogram meters and seconds, this is 0.484 kilograms. And that's what our mass of the object is. So we've now got the mass m. We still need to know the speed v. So recall that the momentum is equal to the mass times the speed, if we would just do the magnitude. And so this means that the speed can be obtained by taking the momentum and dividing by the mass. So that's 11.0 kilogram meters per second divided by 0.484 kilograms. Notice that the kilograms cancel, and so the speed must be given by, let's invert this mass that we found before, so we're dividing by the mass, and now that times our 11 kilogram meters per second gives us 22.72727 repeating meters per second. So we'll just call that 22.7 meters per second. So that's with 3 significant figures as warranted by the problem. All right, so I hinted earlier that Newton's laws can be reformulated in terms of momentum, or that they at least tied into momentum somehow. So Newton's first law, basically we've been saying when the force is 0, then the acceleration is 0. It's more proper to say that if the sum of forces is 0, then the change in momentum is also going to be 0. And in Newton's second law, it's more correct to say that if the net force is not 0, then the net force should be equal to the rate change in momentum, the change in momentum per unit time. So now let's look at Newton's third law. So that one said that force 2(1) equals force 1(2). And so if you basically note that 2(1) is the force from 2 applied to object 1, and force 1(2) is the force from object 1 applied to object 2. And then we say, okay, in a given interaction, maybe object 1 and object 2 apply a force on each other. That means that object 1 will have a change in momentum due to that force from object 2, and object 2 will have a change in momentum due to that force from object 1. And that change in momentum per unit time is of equal magnitude in opposite direction. So the consequence of all this is that collectively Newton's laws imply that in order to change an object's momentum, you have to apply some net force to the object. And forces don't exist in isolation, nor for that matter do net forces necessarily exist in isolation. So there are no isolated changes in momentum. So taken a step further, we've been talking about change in momentum here in the context of Newton's laws. There is actually a name for change in momentum. What that change in momentum is called is impulse. Some people like to use I, some people like to use J for impulse. The change in momentum per unit time is the net force, but the change in momentum, simply put, is impulse. And therefore, if you want to get the change in momentum, you multiply the change in momentum per unit time by the time over which this change is occurring. And so momentum is given by force times time, applied force times the time that it's applied for. And so that is, in both cases, defined as the change in momentum. As with momentum, impulse must be a vector. It is going to have the same direction as the direction of force, and it has the same SI units as momentum does because it is just a change in momentum. So impulse is going to be given by applied force times time, but the force may not always be constant. It may vary instead of being a constant. And the way that we can deal with that, well, you can attempt to use calculus. You can attempt to find the area under the force versus time curve, and that's going to actually give you the impulse. But you can alternatively figure out what the average force is and multiply that by the time, and that will also get you the impulse. So it turns out that the area under this rectangle here should also be equal to the area underneath this curve. So let's look at a few examples of that. So you have some object, and it has a mass of 1.5 kilograms and a velocity of 4 meters per second to the right. And so we want to know what's the object's momentum. Well, we've already done a few momentum examples, so this one is straightforward. You take this mass, 1.5 kilograms, you multiply it by this velocity, you get the momentum. So 1.5 times 4 is 6. So this momentum should be 6, 0 degrees, 6 newtons per second, 6 newton seconds in the 0 degree direction. All right, suppose we now apply a force to the object over some time, and the object's new momentum is 6 kilogram meters per second in the 30 degree direction. We want to know what's the impulse that was imparted to this object. All right, so the initial momentum we found in part 1, just recall that that's going to be mass times the initial velocity. So that was the mass was 1.50 kilograms times the velocity was 4.00 meters per second, 0 degrees, and hence we multiply this by this to get this. Mostly to get this term. The 0 degree term is not changed by multiplying the velocity times mass. Okay, so now we're trying to figure out what the impulse is. So impulse is defined as change in momentum. So that is the final momentum minus the initial momentum. This right here is our final momentum. So this is P final. So again, you could do this graphically by graphing these two, or we can split them into components. So this 0 degree component basically means we have a momentum that's initially like this, and so that's the same as saying that the initial momentum is entirely in the x direction. So 6 kilogram meters per second, 0. Finally, we're moving at a 30 degree direction. So we need to break up like this. So here's the P final. So here would be P final Y, here would be P final X. Here is our 30.0 degrees. So P final X should be P final times the cosine of that angle. And so that will be 6.00 kilogram meters per second times the cosine of 30.0 degrees. So now it's convenient to use the calculator to do this. 6 times the cosine of 30. Cosine of 30 is going to be that square root 3 over 2 term again. So we end up with 5.196. I'll go ahead and keep all of those, some extra figures basically. So we said 5.196. Yeah, 5.196 kilogram meters per second. The final for y is going to be obtained in the same way, but using the sign of the final. And so that's 6.00 kilogram meters per second times the sine of 30.0 degrees. Sine of 30 degrees is just a half, so this is going to be 3.00 kilogram meters per second. All right, so delta P, therefore, is going to be the final minus the initial. So that's basically looks like 5.196 comma 3.00, and then that minus 6.00 comma 0, and then I'm just going to carry the units to the outside here since they all have the same unit. So 5.196 minus 6 should give me negative 0.804. So delta P is negative 0.804 kilogram meters per second, comma, positive 3.00 kilogram meters per second. If I round this off to the correct number of significant figures, this one actually should have been rounded to 2 significant figures, and so this right here actually will end up with to 3 significant figures. This one will have 2 significant figures, would be 0.80. This actually answers the question. This really is the change in momentum or the impulse. However, since we started in polar coordinates, it's usually correct to try to end in polar coordinates. So we can try converting this thing by basically drawing out roughly what the vector looks like. The y part is here, the x part is going this way. So here is our final vector. Excuse me, not our final vector, but our change in momentum vector, our impulse. So if this is our total impulse, this is our y impulse, and this right here is our x impulse. This angle right here we can define as phi, knowing that we want the full angle theta. So theta for impulse is phi plus 90 degrees. So we need to get phi. We can use that the tangent of phi is opposite over adjacent. So that would be 0.804 divided by 3.00. Notice that I've dropped the minus sign because I'm kind of keeping track of that here. So let's see what we get for phi. So we have 0.804 divided by 3. Okay, and then we need to take an inverse tangent of that. Gives us 15 degrees. So what we have so far is phi is about 15.0 degrees, but that means that theta is about 105 degrees. Okay, so now we just need to get the magnitude, and we use Pythagorean theorem for that. with Pythagorean theorem, the signs of these two don't really matter. So this right here is going to give us 0.804 kilogram meters per second quantity squared plus 3.00 kilogram meters per second quantity squared. So let's pull off the calculator again. So 0.804 squared plus 3 squared is 9. Okay, then we take a square root and we get 3.11. So this is basically saying I is about 3.11 kilogram meters per second. So our total momentum change vector, our total impulse vector, is going to be 3.11 kilogram meters per second, comma 105 degrees. And there we have it. We've solved it. All right. Next example, suppose the impulse that we found just above is imparted over the course of 2 seconds. What was the average force exerted on the object? So we basically have established that the impulse was 3.11 kilogram meters per second in the 105 degree direction. So that is the same as the change in momentum, and this change in momentum was imparted over 2 seconds, so delta t is equal to 2 seconds. And we basically can write that the average force times the time is equal to the change in the momentum, or if you will, to the imparted impulse. So we don't really need the vector part. The vector part, the direction part of the vector is going to have to be 105 degrees. It's this part that we start to care about, because we can basically solve for the magnitude by dividing both sides by a delta t. So you'd have I over delta t. That's 3.11 kilogram dot meter per second divided by 2 seconds. And so you end up getting basically a total force of 1.555, and then kilogram meter per second per second. So that's kilogram meters per second squared, and that's the same thing as newtons. So the average force here is basically going to be given by approximately 1.56 newtons. And again, if we are being real sticklers here on significant figures, we would round that to 2 newtons since it's only one significant figure. So there's a question to ponder here. It means I'm not going to really work this out on this video, but I could in principle also ask, or you could in principle ask, how far does the object drift from its original course during these 2 seconds? So I'll just leave that as a question that you can ponder on your own. So going back to Newton's laws as applied to momentum, basically with Newton's third law thrown into the mix, we have that there are no forces in isolation. And that means that every force, and hence every change in momentum, every impulse per unit time, is going to come with a second impulse per unit time, which acts in the exact opposite direction. So the implication of all of this is that a system of interacting objects, we can write that the sum of initial momenta is going to be equal to the sum of final momenta. This is another way of saying that the linear momentum of the system is conserved. So before collision, you might have something like this. At collision, you get some forces applied. After, you might have the two balls moving in totally different directions than they were moving in initially, but if you were to add this momentum and this momentum together, you'd get the same thing as if you added this momentum and this momentum together. That's conservation of momentum. So we now have a second conservation law for physics. The first one that we encountered was conservation of energy. Now we also have conservation of linear momentum. We can see that visually by looking at a Newton's third law force pair. So Newton's third law, of course, says F12 is negative F21. So that's what this is showing. As this force is positive, this one gets a negative direction, and this magnitude match no matter where you go here. So collectively, what that means is if you have two objects which interact, the change in momentum for the first object is equal to, but in the opposite direction of, the change in momentum for the second object. And that's ultimately what Newton's laws, Newton's three force laws or three laws of motion, are telling us, is that momentum is going to be conserved for any system, for any closed system in which all the forces that act on the objects are within the system. As long as there's no external forces acting on the system, there will be no change in momentum for the system. This brings me back to a point that I've made before in these lectures, which is that you have to define your system of interest. And so as long as you have a system of interest which includes only these two objects and there's no net external forces, then the change in momentum for the first object and the change in momentum for the second object will be of equal magnitude in opposite directions. So this diagram is actually showing that. Here is the first vehicle. It's crashing into the second vehicle. Initially, this first vehicle is moving at a faster speed than the second one. They're moving in the same direction. This guy maybe rear ends this guy. And the result is that this guy loses a bunch of momentum, which this guy gains, and that's manifest by this guy now moving more slowly and this guy now moving more quickly. Again, our system of interest here is assuming that the net external force on these two objects is zero. If you add in things like friction and wind resistance and so on, those become external forces to this system. And so, for example, this guy may be slamming on his brakes as he approaches this car, so he's already losing momentum because there is a net external force from friction acting upon this car. So beware of that when defining your system of interest. You have to make sure that there are no net external forces, or if there is a net external force, then that net external force is going to result in a change in momentum for the system. Let's look at an example of this. So we take the two crossover SUVs, these two vehicles that were on the previous slide, and let's give them some actual masses and initial speeds. And let's say that after the collision, we immediately know the first car's speed, that's this guy's speed, and we have to also assume that it is in the same direction. We have to have a direction that this speed is acting in. It's got to be a velocity. The question, though, is what is the speed of the second guy? So we're assuming that basically that this diagram is giving the correct direction for velocities in this problem. All right, so the rule is that the initial total momentum needs to be the final total momentum, because we're assuming that there's no external force acting here. So that means basically that P1 initial plus P2 initial has to be equal to P1 final plus P2 final. And so since the momentum in all cases is given by mass times velocity, this is basically saying that we have mass of car 1 times initial velocity of car 1 is equal plus the mass of car 2 times the initial velocity of car 2 should be equal to mass of car 1 times the final velocity of car 1 plus mass of car 2 times the final velocity of car 2. Now, looking at this diagram, all the velocities are in the same direction, so we can go ahead and drop the vectors here. And we basically are trying to solve for this term right here, the final velocity term. That basically means that we can write mass 2 times final velocity of 2 is mass 1 times final velocity of 1 minus, this is the minus, plus mass 1 times initial velocity of 1 plus mass 2 times initial velocity of 2. So our final speed in this case might look like negative m1v1f plus m1v1i plus m2v2i. This should be 2i there. And then that's over m2. All right, so now we're ready to plug in some numbers. So the numbers, of course, are all given up here. m1, m2. This right here would be v1i. This right here is v2i. This right here is v1f. So let's go ahead and plug those numbers in. All right, so plugging those in, we get the final speed is minus 550 kilograms times 5 meters per second plus 550 times 12 meters per second. We could, I suppose, collect these two terms since there's a like mass in both of them. And so collectively you have 12 minus 5, so this becomes 7.00 meters per second times 550 kilograms. So this means one fewer thing to throw into our calculator. So this plus this divided by this. So V2 final is going to be given by 550 times 7 plus 625 times 4, and all that's got to be divided by 625. So we get a final speed of 10.16 meters per second. So let's go ahead and round it off to 10.2 meters per second. So that is what the final speed of this other car should be. It's worth noting here that I didn't really look at energy considerations in all of this calculation. That is because during a collision, momentum should be conserved. Linear momentum should be conserved. Energy may or may not be conserved for the system, or at least I should say mechanical energy, which is the thing that we can readily calculate, may or may not be conserved. For example, the car or both cars may be deformed slightly. Certainly you're going to hear a noise from the two smashing into each other. Both of those things involve energy being lost from the system, or at least mechanical energy being lost. Certainly energy is lost from the system when the noise is heard, because that's energy in the sound waves which is escaping. So I'm not going to calculate whether it's conserved or not in this particular case right now. You can go do that on your own if you'd like. What I'm going to do now actually is a simple simulation, which is sort of courtesy of the Colorado Physics Education Team. I think it's called sometimes the Colorado PHET, P-H-E-T. This is a simple simulation in which we're going to do a collision between two objects, which is in one dimension. I'm going to go ahead and slow this guy down a little bit before starting. There's a variety of parameters that we can play around with. You can actually see the address of this simulation if you want it. These guys are great people, by the way. They do very nice work. If you want to play around with the simulation on your own a little bit. What I wanted to do, though, is let's start off by looking at this collision in which I have set a single mass that is initially in motion and another mass that has 3 times as much mass and which is initially still. I am showing only the velocity vectors here, and I'm going to go ahead and click this thing that says center of mass, which is this X. And the center of mass is basically, you can think of it as a sort of weighted average of where the mass of the system is. We'll look later at how to actually determine where the center of mass is. And then another thing that I'm going to do is put elasticity at 100%. That means energy will be conserved. So let's go ahead and see what happens here. Pay attention to this mass, pay attention to the center of mass, pay attention to what this mass does. There's the collision, and they're moving off. Notice here what the center of mass has done. So let's restart that. Let's just watch the center of mass during the whole thing. Pow. All right. Center of mass motion actually hasn't changed during this simulation. All right, and now I want to do it again. This time I want to look at the kinetic energy values. The kinetic energy is 0.25 joules before the collision, and after the collision it is still 0.25 joules. So this is all doing with 100% elasticity. Just for fun, we'll put the momentum vectors in as well. That's this little yellow guy. I'm going to take off the velocity vector. So here is the momentum vector. And pow. And if you were to add this yellow arrow to this yellow arrow, they're opposite directions. They should add up to be the same length as the initial yellow arrow and pointing to the right. So one more time. I think that's probably sufficient for the 100% elasticity case. I want to restart now and look at the other extreme, 0% elasticity. Before I click go, those of you who are watching and who want to do something sort of interactive to some extent, obviously I don't have an iClicker on me, and you who are watching from home can't do like a clicker quiz, but here's a quick quiz before I hit play. What do you think is going to happen when these two things collide at 0% elasticity? This is totally inelastic. Elasticity, to some extent, tells us how much energy is being conserved. In other words, at 100% elasticity, we had 100% energy conservation. So 0% elasticity, what's going to happen? Are we going to lose all the energy of the system? Well, let's see. Go, 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 hit. We still have some energy left, and these two are still moving. And in fact, notice that this little X, if we restart it, the little center of mass, continues moving at the same rate that it was before. So what's going on here with this 0% elasticity? What does 0% elasticity mean? Well, it basically, in this case, means how much is this one going to rebound off of this one? If it's 100% elasticity, this one will rebound off of this one such that momentum is conserved. But at 0% elasticity, what we get is, rather than both being stopped at the end, you get that this one does not rebound at all off of this one. They stick together after the collision. And you can think in the very extreme case, what would this be like? And I'll show this extreme case because, as it turns out, I can make this very small and I can make the green one very large. So now the green one is 30 times more massive than the red one. And 0% elasticity, we're still going to end up with these two moving, but as you can see, they're moving rather slowly in this direction. And this is a case where this guy is 30 times as big as this guy. Imagine now that you have something like a rubber ball that you're bouncing off the ground. The ground is another word for the earth. So in previous lectures, we discussed how big the earth was, what the mass of the earth is. It's, let's say, 6 times 10 to the 24 kilograms. Your rubber or bouncy ball is a matter of grams. Let's say 20 grams or 60 grams or something. So 60 grams is 6 times 10 to the minus 2 kilograms. So that's 26 orders of magnitude difference in the mass between the rubber bouncy ball and the earth. So the earth isn't really going to move very much when the rubber ball hits it. And that means that at 0% elasticity, the rubber ball more or less hits the ground and stops. At 100% elasticity, let's go back here and do 100% elasticity in this tiny versus huge case. What's going to happen? Before I fire, think again, what do you think is going to happen? And think this time in terms of the rubber bouncy ball, which is basically going to be bouncing off of the ground. I'm going to actually show the velocity vectors instead of the momentum vectors for this case. Okay, I hope you've got a mental picture at this point of what this is going to look like because I'm ready to shoot. So let's go. Here comes the little guy, hits the big one, it bounces off, the big one's barely moving, and notice what happened here to the velocity vector of the little one. Let's slow the simulation speed down even more. Okay, that's a little too much. All right, so let's see how long this guy is. So it hits, it bounces off, and you notice that this arrow, the length of this arrow is almost the same length that it was, but in the opposite direction as before. So think of that in terms now of the rubber bouncy ball hitting the earth with 100% elasticity. Basically, this would mean that the rubber bouncy ball bounces off with the same speed that it had when it first impacted the earth, which makes sense because the earth is barely going to move. So let's look at a couple ramifications of that simulation of what we basically observed there. For one thing, if the energy is conserved in the collision, then, and you know what the initial velocities are and the initial masses are of the two objects, assuming there's no explosions, anything like that, just two objects collide and then two objects rebound off each other. If energy is conserved, in other words, if you have 100% elasticity, then the velocities are going to be uniquely determined for both objects. And these velocities actually can be uniquely determined even if the collision doesn't conserve energy, so long as we know just how elastic that collision is. So the extreme cases are 100% elasticity, in which case you use conservation of mechanical energy and conservation of momentum together. And you presumably know what the initial velocities and what the masses of the two objects are. So your unknowns are the two final velocities. And you have two equations to work with, one for energy conservation, one for momentum conservation. If the velocities, if the energy is not conserved, then as long as we have some measure of how elastic the collision is, we can still get sort of two equations and two unknowns. Our two unknowns, again, are the final velocities. Our two equations are going to be momentum conservation and some equation that describes how much energy is lost. The extreme case that we have available is 0% elasticity. The two objects stick together, and this is actually arguably the easiest case to solve for, because in this case, the final velocities of both objects should be equal. So let's go back and look at that simulation again just to see how that plays out. I'm going to change the parameters just a little bit from the way that they were before, in that I'm going to make the small one only a fifth the size of the larger one. And you'll notice I've got it at the totally inelastic 0% elasticity. And now we're going to look at what the velocity vectors look like. So let's play and let's see what happens here. You'll probably notice that the two stick together anyway. That being the case, now we see what these two velocity vectors are. These two arrows are actually the same length. So let's go ahead and restart that. And this time we're just going to show the velocity vectors at 0% elasticity. And I'm going to go ahead and make the two objects be the same mass so that we can see this a little more clearly. So ready, set, go. And now they're stuck together and they have basically the same velocity vectors. So let's do that again. This time we'll make the big one very large just for fun. And let's see what happens. We can make the little ones small and go. So they stick together, and if you measure this velocity length and you measure this velocity length, for example, you can use a ruler on your computer screen, you'll notice that these two have the same length, therefore they're moving at the same speed. So this really is the easy case of this collision, because v final 1 and v final 2 are equal. And so if you know what the initial velocities are and you know what the masses of the two objects are, you have only one equation to solve for. The other implication from the simulation, another ramification, if you will, is that, and I highlighted this a few times, the center of mass retains a constant velocity regardless of what goes on in the collision, whether the collision conserves energy, doesn't conserve energy, totally inelastic, totally elastic, any of those, you get the center of mass having the same constant velocity. So the implication is that regardless of what kind of collision you have, as long as there are no external forces, momentum is going to be conserved, even though energy is not being conserved. The center of mass for an object is something that you can find by taking a sort of weighted average of where all the mass in the object is located, or similarly, the center of mass for a system you can find by finding the weighted average position of all the mass in the system. So formally, the equation for doing that looks something like this. If you want to find the position of the center of mass, you take the position of each individual mass in the system, you multiply that by how much mass is in that position, you add all those mass times positions together, and then you divide by the total mass of the system. So you can break that up into an x component, a y component, and a z component. This also works if you have a single object and want to find where all the center of mass of that object is. Although if you have a continuous object of that sort, you end up basically needing to do an integral rather than a sum. So for the general physics course, we would just use discrete masses, individual objects making up a system, in other words. The position of the center of mass then is basically the position of x, the position of y, and the position of z for the center of mass in the system. And we have a related concept to that, which is the center of gravity, and that's usually going to be the same or very nearly the same position as the center of mass. Certainly, if the gravitational acceleration does not vary across the object, then the two should be the same position. And this is basically the the point at which gravity is said to act on an object if you have an extended object. So we'll look a little more at that in the section on statics and on equilibrium and torque. For our purposes, the more interesting thing is that you can also find the velocity of the center of mass. And so here's the equation for getting the average center of mass velocity. It's basically the change in center of mass position per unit time. So that's very similar to finding other velocities we've found. It's a change in position per unit time. And you can basically multiply from the previous slide each of these positions, x, y, z. You can take a delta x over delta t, a delta y over delta t, and a delta z over delta t. And that gets you these three equations, the center of mass in x velocity, the center of mass in y velocity, and the center of mass in z velocity. And so if you want to get the total velocity of the center of mass of a system, you basically can find the x, y, and z components in Cartesian form like this. So that's basically what that simulation is doing in calculating what the center of mass velocity is for a system of two or more particles. So about that, what happens if you have a projectile which breaks or explodes due to some internal forces? For example, here's a rocket. The rocket is moving. It's basically a projectile initially. This is meant to be basically a parabolic arc, although sort of at the edges you can see how it is not. The center of mass is this little red dot, follows this trajectory, and if the rocket were to remain whole, then the whole rocket would basically follow this trajectory. And the idea here is that there's some explosion. For example, with a staged rocket, very often what happens is they blast off the bottom part of the rocket when they've expended the fuel, and then the top part kind of continues on its own way. So before it's a single rocket, after it is sort of separated, but the center of mass actually stays on this trajectory. So if this rocket is in free fall here, then there's an explosion, the rocket breaks up, the center of mass of this thing plus this thing, or regardless of how many pieces, the center of mass will stay on this trajectory. So the range of this rocket as a whole will end up being the range of the center of mass. So let's do a little example with that. Let's take a simple two-stage rocket, and we give the whole rocket a mass of 10,000 kilograms. So the first stage is released after expelling the fuel and lands 100 kilometers from the launch point. So, here's our rocket. It's going. It runs out of fuel here at the apex, and if the whole rocket stayed together, then it would have landed here. The back half of it is blasted off and lands only 100 kilometers from where the rocket took off at. We'll call that half the total distance of the center of mass, and we want to know where the second one is going to land. This is assuming, of course, that there's no further propulsion in rocket number 2. So this actually is a fairly straightforward problem. The center of mass should have landed right here. So this is 100 kilometers away from the beginning. We're going to assume one thing, which is that the two halves of the rocket have equal mass. If that's the case, then they should land equal distances away from where the center of mass was going to be. Or they should have, if this one goes to 0 speed, then this one's speed should double. And since this is at the apex, the entire velocity is in the x direction. So that means that this one will end up going an additional distance d away, and so the total distance should be 300 kilometers from where this thing was launched. So while we're on the subject of rockets, how do rockets work? Well, a rocket basically contains some amount of fuel internally, which it heats. That fuel basically ignites, it becomes a gas, and it's sort of forced out the nozzles on the back of the rocket. And in order for that to happen, some force exchange happens between the rocket body and the fuel that's being exchanged. So the fuel that's being exchanged is given a net change in momentum in this direction. The rocket's being given a net change in momentum in this direction. And that's basically happening by two things. One is that there's this force exchange that is causing the mass that's in this rocket to gain velocity in this direction. The other, however, and in some ways this is the bigger effect, is that some mass from the rocket is being ejected in this way. And so the rocket's mass has decreased. And if you need to have momentum be conserved, which you do, then by decreasing the total mass of this rocket, you have to increase the velocity of the rocket to make up for that, so that the total momentum is constant. And of course, you can have some additional external forces on the system like gravity, which will change the momentum. So let's look at how rocket propulsion is going to work. So there's basically going to be three factors which matter. There's the exhaust speed with respect to the rocket. We'll call that VE. And it turns out that the practical limit for a conventional non-nuclear rocket is about 2,500 meters per second of relative speed. So if this rocket is already moving at 2,500 meters per second, then this ejected fuel will actually be stationary with respect to whatever observer sees the rocket moving at 2,500 meters per second. So that's the first factor. Second is the rate at which mass is being ejected from the rocket. Sometimes this is called the burn rate. It's basically delta M over delta T. And that's related to a thing that's called thrust. And thrust basically combines this factor and this factor. So thrust is this exhaust speed relative to the rocket times this burn rate. And then the last thing that has some effect is the total mass of the rocket. The total mass of the rocket is given by, say, M. And so as some fuel is being ejected, then the mass of the rocket that's actually moving forward is whatever the initial mass was minus the amount of fuel, the mass of the fuel has been ejected. And so the acceleration basically is given by the force, which thrust is actually a measure of force. So it's given by thrust divided by the mass of whatever's left in the rocket minus whatever the acceleration due to gravity is if the rocket's being launched straight up. Okay, so this is telling us basically that the more massive a rocket is, and remember that this mass includes the rocket's fuel, the more massive the rocket is, the less the acceleration can be, but the larger the burn rate or the larger the exhaust speed relative to the rocket, the greater will be the acceleration. I should probably note here that this equation makes one kind of important assumption, which is that the rocket itself is relatively heavy, relatively massive compared to the amount of fuel that is leaving from the rocket. if you have a single stage rocket, that basically means you've got fuel in this stage, and when this stage runs out of fuel, you're done. There's no further acceleration. Then you can figure out what the terminal velocity is going to be. Excuse me, I should call this the final velocity, assuming no drag on the rocket. This final velocity basically you can obtain from the exhaust speed times the logarithm of the total mass divided by the mass of the rocket without the fuel. So you can actually use this to solve for the maximum mass of the rocket versus the total mass of the rocket and fuel, meaning basically how much rocket can you get given some amount of fuel if you want to escape from the Earth. So we solved for the escape speed of the Earth back in the lectures that covered energy conservation. So you can use that then to plug that in for this V and then solve for how big should the rocket be with respect, the rocket loaded with fuel, that is, with respect to the rocket without fuel in order to make this escape speed. All right, let's look at one final example. This is a Saturn V rocket, which consists of several, actually 5 F1 rocket engines. So this right here is the F1 rocket engine. I'm actually standing in front of it with my daughter for a sense of scale of how big this thing is. And then this right here is the whole Saturn V rocket. It has 5 of these engines. These are the little nozzles down here, is actually this engine. And this basically, I visited this, is one of the NASA facilities. It's actually in Mississippi along the freeway as you leave Mississippi into Louisiana. So you too can go visit that if you take a little road trip. In any case, let's say that we have a certain burn rate, a typical exhaust speed, and an initial mass. Let's figure out what the initial acceleration of this rocket. We're calculating the initial acceleration and the thrust. So thrust was T, and that's actually this part of the equation. So let's do the acceleration first before I go circling everything in the equation. So the initial acceleration should be the fuel burn rate is 14,000 kilogram per second. This right here corresponds to delta M over delta T. The typical exhaust velocity is always given with respect to the rocket. So this right here is the V sub E, and then this right here is the initial mass M. So this initial acceleration should be 2,400 meters per second times the burn rate, which is 14,000 kilogram per second, divided by whatever the initial mass is, 2,800,000, so 2,800,000 kilograms, minus g, which is 9.80 meters per second squared. All right, so I'm going to go ahead and also calculate the thrust now that I've written that all down. This right here is the thrust. So the thrust should be 2,400 meters per second times 14,000 kilograms per second. You'll see why I'm calculating the thrust first is because it's part of this term for the acceleration. So 2,400 times 14,000 gives us this as our thrust. This is 33.6 million newtons. Notice meters per second times kilograms per second gives us kilograms times meter per second squared, so that should be newtons. So this we'll just put as 3.36 times 10 to the 7 newtons. So that answers this part of the question. All right, and since that was these two terms here in the numerator, what we need to do is basically take that number now and divide it by the 2,800,000. So that gives us 12, and then that's basically, you could think of that as the upward acceleration. So we also have a downward acceleration from gravity, so minus 9.8, and you get 2.2 meters per second squared. So this initial acceleration is only 2.2 meters per second squared. Notice that if you're able to maintain a constant burn rate, that as this mass begins to decrease, this number that goes in the denominator will start decreasing. Basically what I'm getting at, in other words, is that in order to solve for the acceleration sometime later, you're probably going to need to use not only calculus, but in fact a differential equation. The other thing to note is that you could rearrange this equation to see what's going on a little better. So we have a sub I is equal to basically VE delta M over delta T all over M minus G. So I'm just rearranging this equation a little bit. If I multiply everything by M, I have M A sub I is equal to VE delta M over delta T minus mg. And this is just Newton's second law, because this term right here is the thrust term. This term right here is the force from gravity. And so this is basically saying sum of forces is mass times acceleration, where the sum of forces in this case are given by the thrust and gravity. And since the thrust is upwards and gravity is downwards, hence we have this minus sign in here. So that's where this equation is actually coming from. All right, so that is it for momentum itself. We've looked at quite a few topics here on this first part of this lecture set. We've now introduced the topic of linear momentum, of impulse as change in linear momentum. We've seen the idea of the law of conservation of momentum, and we've looked at rocket motions, both in terms of center of mass motion and in terms of thrust. So at this point, I am just wanting to say thanks for watching, and I hope that you found this video helpful, and I look forward to discussing it with those of you who I'll be seeing in class this next week. So farewell for now.